In this video I want to look specifically at the method for calculating changes in height during vertical circular motion. So this is really going to be used when you're working out changes in gravitational potential energy. And the way that you calculate height when the particle is not at either the top or the bottom. Usually situations start with the particle either at the top or the bottom, or it don't have to, but when you're just going from top to bottom and just those two places, those two positions, it's very straightforward to calculate changes in height. But when the object is at some other position around the circle, it can be a bit trickier until you've seen it once, and then it's fine. But just wanted to run through that quickly. So imagine, although it's the same in the case if you're starting at the top of the circle, but I want to imagine that we're starting at the bottom of the circle with some given speed u down here. So an initial speed there, u at the bottom, and then we're interested in perhaps, calculating the speed at this new position somewhere on its journey around the circle at a general point around the circle. So we'll have a velocity v at this general point here. And the way we would measure that point typically would be by how far, what angle the radius has gone through from the bottom to this general point. So we're looking at an angle of theta as the means of measuring, specifying the position. And so if we want to calculate change in gravitational potential energy for a situation like this, from the bottom to a general point with an angle theta, then obviously what we need to know is we need to calculate h. So h might be, for example, up to that level from the bottom of the circle, and clearly I can transfer that h there over to here. That would be the same h, and then we need to think about how could I find some sort of expression or some method for calculating what that h there is. And it's fairly straightforward, bit of trigonometry obviously. So what we're looking at is those levels there being the same, and then clearly what we've got here is a nice right angled triangle with r, the radius, as the hypotenuse of this right angled triangle. And of course the blue dotted line from the center of the circle down to the starting position there, that is also a radius here. So what we've got in order to calculate h is we've got h as r minus whatever this gap here is, this bit, this section here. H is going to be the radius minus whatever that bit there is. So that's really the crucial thing that I need to work out, and we can do that with a nice bit of simple right angled triangle trigonometry on this right angled triangle here. And so clearly that gap there must be r cos theta, and so that gives us a nice way for calculating the change in height. We'll typically be trying to, this is likely to come up if we're wanting to calculate the change in gravitational potential energy. So if I was calculating change in GPE here, obviously that's just going to be mgh, and I need some kind of way of calculating, way of finding out what h is, and we can do that now from our diagram. So where h is just going to be, so it started a full radius from the below the center of the circle, and at this new point it's now just r cos theta, radius times cos theta below the center of the circle. So the change in height there has been r minus r cos theta, and very often you'll see that as a factorized expression. So we might well have here h as r brackets 1 minus cos theta. And then that expression there can get substituted into the formula for the gravitational potential energy. So therefore, delta GPE, oops, sorry, that was it. It's supposed to be a delta there, it's come out a bit weird. Delta GPE is going to be mg, and then instead of the h, we're going to have this new expression, r brackets 1 minus cos theta. Just a quick word about that. You might say, well, you've positioned this below the midpoint level of the circle, which is why we're subtracting something from r in order to calculate that. But if you think about how this function, this expression behaves for different angles of theta, clearly if theta is 0, then that would be with the particle at the bottom of the triangle. Theta equals 0 would be, sorry, at the bottom of the circle, beg your pardon. Theta would be 0 when the particle is down here, and of course cos theta, when theta equals 0, cos of 0 is 1, so we get 1 minus 1 in this bracket, and the change in gravitational potential energy becomes 0. When we are at the midpoint, the halfway point, so the particle is level with the centre of the circle, we've got theta is 90 degrees there. And of course, cos theta, cos 90, beg your pardon, cos 90 is 0. So we've got 1 minus 0 in the bracket, giving us just 1. So the change in gravitational potential energy is just mgr, with the change of height of the full radius. And as we go above that horizontal position, up into the top half of the circle, then we've got theta being greater than 90, somewhere between, for example, 90 and 90 at the horizontal position, and then up to 180 at the top of the circle. And in all of those cases, cos theta is a negative quantity. So I'd be, for example, when it's 180, I've got negative 1 for cos theta. Cos of 180 being minus 1. So there I'm doing mgr, and in the bracket I've got 1 minus negative 1 now for my cos theta. So that's giving me 2 radiuses as the change of height. So the cos function in here handles very nicely that change in, with the change in sign, handles very nicely the ability to go more than a 90 degree angle around our circle. And the maths works it out very nicely for us. Clearly, it's a similar sort of process for dealing with something where the object starts at the top of the circle rather than at the bottom. You're going to come out with an identical expression, essentially. Slightly more tricky is if the object starts somewhere which is not at the centre of the circle. Sorry, not at the either the top or the bottom of the circle, but somewhere on its already round its circular path, if you like. If it starts at some other angle, that gets slightly more tricky. But essentially, the most straightforward way to do that would just be to calculate the change in height from either the bottom to the starting position, and then from the bottom to the new finishing position. And then see what the difference between those two is, or obviously a similar approach from the top. So there we are. There's an expression, a way of finding out changes in gravitational potential energy and changes in height when the object is not positioned at either the top or bottom of the circle. mgr brackets 1 minus cos theta.